So, question 4 on page 438 talks about a couple of helicopters. It says that the position vector, so the position of two helicopters, x and y at time t seconds, are given by the formulae, and then there's two vector equations given there, which I'll write down in a second. So you're given a vector equation for helicopter x and a vector equation for helicopter y. And the first thing you're asked to do is to find the speed of the two helicopters. So let's have a look at helicopter x first. And we're told that the r vector for helicopter x is 11, 3, negative 3 plus t times 1, negative 1, 4. So that's our vector equation. And we need to find the speed. So just in terms of common sense, I suppose, if speed is meters per second, then if we can work out how far it travels over the length of 1 second, then we're good to go, aren't we? So the easiest numbers to use are t equals 0, i.e. where is the helicopter at 0 seconds, and t equals 1, i.e. where is the helicopter after 1 second. I could have used t equals 9 and t equals 10. I could have used any two pairs of consecutive integers, and that would have been fine. So, but 0 and 1 will give us the easiest solutions. So at t equals 0, what do we have? Well, we have the r vector for the x helicopter is equal to, well, if t is equal to 0, then this whole vector just disappears, doesn't it? Because 0 times 1 is, well, it doesn't disappear, but it becomes a 0, 0, 0 vector. In other words, the 0 vector. And so we're adding 0 to each of the components of the position vector here. So we end up really just getting 11, 3, negative 3. And at t equals 1, then r vector for the x helicopter is equal to, well, if t equals 1, then I'm just going t times 1, sorry, 1 times 1 is 1, and 11 plus 1 is 12. Then I'm going 1 times minus 1 is minus 1, and 3 minus 1 is 2. And then I'm going 1 times 4 is 4, minus 3 plus 4 is equal to 1. So that is the vector after 1 second. So we've got one vector at 0 seconds and one vector at 1 second, and therefore, because we've got two vectors, we can work out the distance between them. So graphically, from this point here, we've got one vector here, if this is the pathway of the helicopter, and one vector here, that's at t equals 0 and t equals 1, then what we're interested in is this distance here, because that'll be the distance covered by the helicopter over a second. Okay, so we just work out the distance. Now, I just wanted to point out for those of you who just love formulas that on page 418, there is a distance formula between two vectors that are sort of diverging from an origin. And the distance formula is distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And so you could use that. I don't like it. I just think it's an extra formula to learn, and I'd rather sort of do it based upon my essential understanding of how vectors work. I'd rather solve it that way every time rather than put a formula in, which is just another thing to look up, I suppose, or another thing to remember. Whereas if you understand what's happening to get the distance formula, I reckon that's better. That's just my personal opinion. Use it if you want to. I'm not going to. So there. So what is the distance then? So therefore, distance travelled. So looking at it from a vector perspective, we can see that this distance travelled here, in relation to the two vectors that we do know, we could get this vector by travelling down this vector and then travelling up that vector. Alternatively, you could travel down that vector and go up that one. But I'm going to go this way. So travel down and then travel up. So it's the negative of this vector plus this vector. Okay, and the distance is going to be the magnitude of the resultant vector. So I'm going to go straight into putting my magnitude signs down, and I'm going to say take the negative at t equals 1, so that's 12, 2, 1, add the vector at t equals 0, which is 11, 3, negative 3. So there's my two vectors. I'm now going to add those two vectors together to make a resultant vector. So that's going to be 11 minus 12, which is negative 1, 3 minus 2, which is 1, and negative 3 minus 1, which is negative 4. There we go. So our resultant vector is negative 1, 1, negative 4. And that's is equal to negative 1 squared. Notice I'm putting brackets around my negatives, plus 1 squared plus negative 4 squared, and the whole thing is square rooted. And that's equal to the square root of 18. And we'll rationalise that to 3 root 2, because 18 is 9 times 2, and the square root of 9 is 3. So, i.e., speed is 3 root 2 meters per second. It doesn't say whether to make it exact or not, so you could go 2.45 meters per second to 3 significant figures. Any questions there? That's all right, isn't it? That's not too bad. We just need to repeat it for helicopter Y. So for helicopter Y, we have the R vector for the Y helicopter is equal to 1, negative 7, and negative 2, plus T times 2, 1, 9. I'll go through this one a little bit faster now that we've sort of seen the same process here. So when T is equal to 0, the R vector is just that position vector, 1, minus 7, minus 2. And at T equaling 1, we have the R vector for the Y helicopter being, let me see now, we've got 1 plus 2, which is 3. We've got minus 7 plus 1, which is minus 6. And we've got minus 2, we've got minus 2 plus 9, which is equal to negative 7. Let's get rid of that little dot there so it's not confusing. Okay, so that's our two position vectors, I suppose, over the course of 1 second. So I'll do the same thing with distance. Therefore, distance travelled over 1 second is 1 minus 7 minus 2. Sorry, negative of that, plus 3 minus 6, 7. Okay, again, I'm doing the negative there for the same reason. I know this is a different diagram for the other helicopter, but it's the same idea in that to get this distance here for the second helicopter, I'm going down here and then up here. This vector down backwards plus this vector is going to be equal to this vector. So that's why I'm doing the negative there. And that is equal to, so 3 minus 1 is 2, minus 6 minus negative 7 is plus 7, so we're left with 1. And 7 minus negative 2 is 7 plus 2, so it's 9. So we have a vector of 2, 1, 9. And then I will square the components. They're all positive, so I don't need any brackets, like so. And that gives me the square root of 86 as being my final answer there, which I don't think can be rationalized. I don't think there's any square number that will go into it. And again, we can conclude, i.e. speed is the square root of 86 meters per second, or what have I got here? 9.27 meters per second to 3 significant figures. Right, I'll need to move slides in a second to do the next 2 parts in 5 minutes, which I can do. Does anyone have any questions before I move on? No such thing as a stupid question, just a question unanswered is pretty silly. No, okay. So question 2B is where I diverge from the textbook solution, just FYI. So let's just frame it up first, understand what we're looking at, and then I'll explain how we solve it. So question 2B says, show that the 2 helicopters do not meet. So B, show that they do not meet. So we're told that they don't meet, we need to show it. So in other words, if you show that they do meet, then there's something wrong. Okay, so what does do not meet mean? So I just want to do it graphically for a second. Don't worry about the 3D-ness of it, or the lack of 3D-ness, I should say. So what it's really saying is that the helicopters are going to go along 2 pathways. So if there's a point of intersection, then all that means is that the 2 lines cross over each other. Remember, there's skew in 3D, which means they may pass over each other, but if there's a point of intersection, then they literally cross over each other. So that's point number 1. But it says here, it doesn't just say, show that the paths of the helicopters do not meet. It doesn't say that at all. It simply says, show that the helicopters effectively don't crash into each other. So not only would they have to have a point of intersection, but the point of intersection would have to be for the same value of t, wouldn't it? In other words, the paths would have to cross over each other at the same time for them to crash. Does that make sense? So we need both of those things. So keeping that in mind, this is what we're going to do. So I'll just put that in there, at the same time. So we'll just write that as a little expression there. Okay, for helicopters to meet. No, I'll just do it slightly differently actually. I'll say if the helicopters meet, then there is a point of intersection for some value of t. Is that okay? There's a point of intersection for some specific value of t. That's what that means. So the way I'm going to show that they don't meet is prove the converse is not true. So if I can show that assuming that they meet, we get some ridiculous values for t, then it must therefore be that they don't meet. Okay, so it's called proof by contradiction. If you can contradict it, then you can prove it. Okay, I'm going up to slide 10 now so that you can see the working out there. So what am I saying? I am saying, i.e. Rx, so the R vector for the X helicopter must equal the R vector for the Y helicopter for some value of t. Alrighty, so let's set them equal to each other. So we've got 11, 3, negative 3, plus t times 1, negative 1, 4, equals 1, negative 7, negative 2, plus t times 2, 1, 9. So I'm just setting them equal to each other, and I'm allowing t to be exactly the same on both equations because I know it has to be at the same time. In the solutions for the textbook, it makes this t and makes this s, and then goes along and proves it as if there was a point of intersection. Okay, so this is where I diverge. So if I now just simplify the left-hand side and the right-hand side, I get 11 plus t, 3 minus t, and negative 3 plus 4t equals 1 plus 2t, minus 7 plus t, and minus 2 plus 9t. Okay, so I've got a vector on the left-hand side and I've got a vector on the right-hand side. So rather than equating all three components, I'm now just going to do it one at a time, and you'll see why in a second. So equating the x component, I get 11 plus t equals 1 plus 2t. Now, if I subtract t from both sides and subtract 1 from both sides, I will get 10 on the left-hand side and t on the right-hand side. So I get 10 equals t. Now, if I equate the y component, I get 3 minus t equals negative 7 plus t. Now, if I add 7 to both sides, I get 10. And if I add t to both sides, I get 2t. And therefore, I get t is equal to 5. Okay, so what does that mean? That means that if the two vectors were equal, I would have different values for t for the x and y component. Okay, that's all I need to say. Since value for t is different, they do not meet. See how I did it by contradiction? So assuming it's true, t doesn't work out, therefore it can't be true. Okay, it is 11:26, which is time to stop. So what I might do is I might leave part C as an exercise for you to finish off there, which is simply to find the distance between the helicopters when t equals 10. So you literally just substitute the value of 10 in for t, work out the two resultant vectors at that point, and then work out the distance between them. So it's relatively straightforward, stuff we've done before. So I'll leave it there, and yeah, we'll do some more revision work over the next 2 lessons. Thank you very much.